Hello, and welcome to our Capstone team presentation. Our industry partner is JB Hunt Transport, a Fortune 400 company located in Lowell, Arkansas. We are lucky to be working with Doug Mettenberg, the Vice President of Analytics, Becca Lugin, the Director of Engineering and Tech, and Kyle Cratchley, a data scientist for the company. Our team is led by Madeline Suellentrop, our project manager, and comprised of Garrett Clark, Chase Cottrell, Nicholas Jaco, and Jaclyn Walls. JB Hunt has asked us to improve the accuracy of their total route cost calculation process for multi-stop truckload shipments. These shipments start from the same origin and are dropped off at various destinations using only one third-party driver and one truck. Within our presentation, we'll explore the segment of JB Hunt that we are working with, the areas of concern, our evaluation of the current system performance, our solution to the error within the system, and the impact our model will have on JB Hunt. To start us off, I'll talk more about our position within JB Hunt. JB Hunt possesses the largest company-owned trucking fleet in the nation and executes the shipment of freight through truckloads and rail partnerships. There are 5 divisions within JB Hunt that provide different functions to accomplish this. Intermodal deals with train shipments, and DCS ships through JB Hunt-owned trucks. Final Mile delivers to customer residencies, also using company-owned trucks. Truckload consists of JB Hunt trucks traveling longer distances than normal. However, our project is relevant to the ICS division, also known as Integrated Capacity Solutions, which is responsible for the non-contracted orders that flow through JB Hunt. The ICS division takes these non-contract orders and provides a competitive shipping rate using company-owned rate calculation software called ETP for the customer to consider in a bidding process. Maddie will now elaborate more on JB Hunt's multi-stop truckload transportation.
Thanks, Chase. So multi-stop transportation is used to consolidate multiple customer orders into one shipment. As you can see in the graphic, there are 3 orders, green, yellow, and blue, from the same customer with the same origin of bondurant in 3 different destinations corresponding with each order. With multi-stop transportation, all of the orders can be delivered with one truck and one driver, as can be seen on the top half of the screen. Whereas with direct shipments, it takes 3 drivers and 3 trucks to complete all 3 orders, as seen on the bottom of the screen. So ICS currently is responsible for planning 4 types of transportation routes. So one of these is the multi-stop routes. And then there's truckload routes, which are for shipments that use a full trailer. Intermodal shipments are too large for a trailer, and they can also be used for international shipments. And then less than truckload, which is for shipments that are too small for a full trailer. So multi-stop combines multiple less than truckload routes into one multi-stop route. According to a research paper published by Dr. Rossetti and Dr. Zhang on multi-stop truckload planning, this transportation method is becoming increasingly popular due to potential cost savings and shorter transit times. For example, by combining these 3 orders into one multi-stop shipment, we can reduce the total distance driven in order to successfully deliver these 3 orders, which will in turn reduce the total time on duty for the drivers. So reduction in labor hours reduces overall costs. In order to calculate the cost for these multi-stop shipments, JB Hunt uses their ETP application, which I will talk about with the next slide. So JB Hunt's ICS division uses their Enterprise Transportation Planning application, or ETP, to calculate shipping costs for their customers. After a demonstration of ETP from Eric Schauer, a data scientist at JB Hunt and ETP's product owner, we were able to break down the steps of the process into a swim lane diagram. We used a swim lane diagram because we were able to identify the key roles in this process and their specific interaction with ETP. So to explain this process, first, the startup team within ICS receives the details of an order through their electronic data interchange system. Then this order information consists of the number of stops to complete the load, their intended arrival date, the pickup location and time, and the load weight. The order details are formatted into a customer request, and then those customer requests are put into their database, LTL Consolidator. Then one of ICS's logistics optimization specialists sends a batch of customer orders from the LTL Consolidator to ETP. ETP then computes the cost of shipment for all JB Hunt offered transport methods, so less than truckload, intermodal, and truckload. Then ETP groups orders together with the same origin or destination. So when we spoke with Eric Schauer, he explained that the Clark-Wright method is then applied to find feasible multi-stop routes. After this, a load plan is made for each type of transportation method, which will include the multi-stop load plan if any feasible routes are found in that previous step. So these load plans are given to the customer for them to select a route. Once the customer chooses a route, it is booked as an order, and then the order is made visible to the rest of JB Hunt. So now Nick will dive into the equation used by ETP to calculate these multi-stop truckload costs.
Thanks, Maddie. So together with JB Hunt, we identified the concerns associated with ETP, and from that discussion, we learned that JB Hunt has not significantly analyzed ETP's accuracy since its creation approximately 10 years ago. Therefore, there are factors that are outdated in ETP's current calculations. As you can see from the equation, the current rate calculations are pretty simple. ETP uses the current market rate per mile to the final destination and multiplies it by the total miles of the trip, and then adds stop-off costs. And stop-off costs are specific to multi-stop loads and increase as the number of stops increase. And then the whole equation is multiplied by JB Hunt's profit margin. So going off that route example from the previous slide from Bonnarott to Little Rock, the rate used would be the market rate for Little Rock multiplied by the total miles on the route. This brings up our first concern. The rate does not consider the other two destinations, only the one to Little Rock. Then ETP adds a stop-off fee for a 3-stop route. So our industry partner believes these fees are inaccurate and they increase proportionally with each stop, which does not represent the increase in uncertainty with each stop. Finally, ETP multiplies the current calculations by JB Hunt's profit margin. So next I'm going to dive into the inaccuracies of ETP. So JB Hunt gave us 22 months of data dating from January 2019 to October 2020. And we're only going to be focusing on truckloads and shipments from a single origin. So we had to do some data cleaning in order to focus on a more precise data set and excluded the outliers and incomplete rows of data. So once we cleaned it, we gathered a total of 3,600 rows. And given our data set contains that many rows of orders with estimated costs and actual costs, we will use error as estimated cost, actual cost minus estimated cost as seen in the equation below our histogram as our key performance measure. So in addition to the columns shown in this graphic, we were also given data on our predictors such as weight, delivery and pickup date and time, miles, total number of stops, and number of customer orders, but we're going to talk about the importance of those later. So from the predicted error, which is again actual cost minus the estimated cost, we are able to conclude the mean absolute error, the total absolute error, and the mean absolute percent error. So our goal is to get the mean absolute percent error down to around 10%, which will significantly improve ETP's performance. From our data, we learned that they overestimate their predictions 48% of the time and underestimate their predictions 52% of the time. So on the graph, you can see a histogram depicting the predicted error against the frequency. So generally speaking, the data is normally distributed and the average error is close to 0, which means that the ETP software is accurate, but JB Hunt wants it to be more precise. So we created a normal probability plot using the Kolmogorov-Smirnov test, and we did not find any evidence to reject this normal distribution. So next, Garrett's going to talk about where we found error in our data.
Thank you, Nick. So inside the cost equation, we evaluated the variables total miles and rate per mile. The visual on the left depicts a trend we found within our data set for total miles, which is that as the total number of miles on the shipping route increases, the error per mile that is associated with that route decreases. This is because that longer routes must travel greater distances on highways and interstates, more than shorter shipment routes, which spend more time driving within city limits. Traveling on highways is more certain when it comes to calculating the cost of a shipment because the speed of travel is much more consistent. When it comes to error, total miles on a shipment route does not impact the associated error within an order, which is proven by the trend line on the left. Now I'll speak on issues with another variable that is used in JB Hunt's cost equation, total stops and their associated fees. Currently, ETP's cost equation uses the market rate per mile for its cost estimations. The rate per mile that has been used in previous orders is not stored, so that information was not available to us in our data set. However, we were able to use the other columns in our data, and by using equation 1, we were able to calculate the market rate per mile for each row. We do not know JB Hunt's process for calculating the market rate per mile, and our industry partners did not find it important for us. and we were encouraged to focus on using the transcore rate rather than the market rate for further analysis. JB Hunt uses the DAP Freight and Analytics Network to get the transcore rates for a given lane. These rates reflect real-time market supply and demand at the time the order is booked. JB Hunt currently does not utilize the transcore rate as best they could, despite having a lower mean absolute percent error than the market rate. As shown in the figure to the right, we compared the mean absolute percent error of ETP's cost predictions using the market rate per mile versus the transcore rate. The current mean absolute percent error when using the market rate per mile was calculated to be 20.13%, but when we substitute in the transcore rate, the mean absolute percent error fell to 14.15%, resulting in a difference of almost 6%, showing that the rate per mile is causing prediction error. Now I'm going to explain why multi-stop truckloads are preferred over direct shipments. So using a multi-stop truckload option as opposed to direct shipment significantly increases the amount of uncertainty that a carrier will experience en route. Based on opinions from almost 50 different truck drivers on Trucker Path Blog, they concluded that this uncertainty is likely made up of factors such as human error, unforeseen forced breaks due to regulations set by the Department of Transportation, or unpredictable schedules of pickup or drop-off locations. When planning routes and cost predictions, ETP cannot take into consideration the effect that human error has on the success of a multi-stop route. A trend within our data shows that as the number of stops increase, the percentage of error associated with that trip is also increased. We found examples in our data set to illustrate this point. We compared 3 trips that had very similar load descriptions, with the exception of the number of stops, to show the impact that total number of stops is having on the error generated within ETP's system. I'm now going to hand it off to Jaclyn, who's going to go into stop-off fees and the trends that we found in our data associated with them.
Thank you, Garrett. From our research on the previous slide on stop-off fees associated with a multi-stop shipment from Clearfield, Utah to Carson, California, our group thought it would be best to start looking at the entire data set and evaluate all stop-off fees. As you can see in the chart, we've displayed an example of one company's stop-off fees. And according to Becca Luchin, the process of assigning stop-off costs are agreed upon between JB Hunt and the company in contract. Each company has a different set of stop-off costs that are unique to their contract with JB Hunt. To understand how stop-off fees are assigned, it is important to note that the pickup stop and first delivery stop are quote-unquote free, which means stop-off costs aren't really being assigned until a route has multiple deliveries. Our industry partners also informed us that these fees were chosen using tribal knowledge, and there was no real data analysis done to calculate these numbers before they were agreed upon. Therefore, we believe the stop-off costs assigned do not reflect the error caused by additional stops. In the graph, you can see the relationship between the fees per stop and the error in ETP's prediction. The overpredictions tend to increase when additional fees are attached to the route in correspondence with an increase in the total stops. So for this example, at 6 stops, there is on average an overprediction of $588, and that is made even worse by the $375 stop-off fee. Once we identified this error in our system, we wanted to start improving the process. And to begin going about this, we looked into using multiple linear regression, which I will elaborate on next. So beginning the process of improving the cost prediction, we started with a multiple linear regression analysis just because of the simple nature of the current equation. We saw multiple linear regression as this good starting point because it outputs an equation that's a simpler addition to ETP's current process, rather than trying to change multiple pieces of the equation. Using the data set, we performed the multiple linear regression analysis to identify significant predictors of actual cost using Minitab. These predictors consist of known information that JB Hunt receives with each customer request. Because of the large nature of our sample size, when initially running the multiple linear regression, it wasn't really surprising to any of us that each one of the predictors had a p-value of 0, indicating that it was a significant predictor. However, what we did find surprising was a high VIF value that showed multi-collinearity between some of the factors. We removed these factors and ran the test again, still finding all variables to be significant. So within our multiple linear regression, we had 4 continuous variables, which were miles, stops, stop count, weight, and customer order count, and then one categorical variable, which was equipment type with 3 different levels: dry van, flatbed, and reefer. These 3 different levels had different baseline coefficients and therefore were acting as different functioning equations. From these different equations, we were able to find the coefficients for each of the different numerical predictors we were using. And after doing our multiple linear regression analysis, we did realize that there were some issues being presented within using this model. First, the performance of the model was poor with a mean absolute percent error of 22.9%. And as mentioned previously, there were issues with multi-collinearity, and we also found that there were issues with normality. And these are all key assumptions while using this type of multiple linear regression model. Additionally, the R squared was performing at 68.9%, and we could conclude with 95% confidence that there was a lack of fit issue. So therefore, we moved on from looking into multiple linear regression and started looking towards machine learning, which Nick will talk about next.
Thanks, Jaclyn. So when we shifted our focus to machine learning, we began modeling a random forest regression within Python. So a random forest is a collection of multiple decision trees, and decision trees are a type of model that is used for both classification and regression in machine learning. They send you down a certain route of the tree to what we call the branches that yield us a specific result given the factors for that predictor. It's going to do this for each predictor in the tree. So we chose this method due to the large amount of data we were dealing with. The large data set provides a large random forest and supplies the machine with many order samples to train with and learn from. So a random forest is simply a collection of all the decision trees in the forest whose predictions are all averaged into one result and giving us, in our case, the predicted cost. So they're pretty powerful models because they can limit overfitting without substantially increasing error due to bias, and can also reduce the variance of the model by training itself on multiple samples of data. So as you can see in our diagram of our random forest, each customer order is its own decision tree that outputs its own prediction using the specific variables associated with that order. So it will do this for every order in our data, average out all the predictions, and give us a final prediction for the entire random forest. So we chose to use Python and not another programming language because it's a simpler language when compared to other programs like R or C++, and also because of how easy it is to use for data manipulation and that it was recommended to us by our partners. So next I'm going to give a quick breakdown on how the decision trees operate within our random forest. So decision trees have the characteristic of being pretty simple to understand and easy to interpret. And as you can see in the graphic, each decision tree correlates to one individual customer order. So the variables or predictors associated with the order form the branches of the tree, which further extend to the machine deciding if the variables are high, low, or right around the average. The machine will then learn, hence the name, from each tree and its associated actual costs in the training set of data. So the more trees, the bigger the data size the model has to learn from, the more precise the model is going to be. Given the size of our data set, we considered this the correct approach to computing our estimates. So decision trees can handle both categorical and numerical predictors, but decision trees within random forest paint an entirely different picture. So I'm going to let Chase bring you up to speed on that.
Yeah, thanks, Nick. So in the past, multiple linear regression made it difficult to use categorical variables because every level of a categorical variable has a different equation. Equipment had 3 levels for 3 equations, but some of our categorical variables had up to 500 levels. In our basic random forest, we had trouble handling categorical variables in our code for their data type issues. Kyle Cratchley, a data scientist at JB Hunt, provided advice that helped us implement these pipelines into our code. It is used to chain together multiple estimators and automate the machine learning process. Pipelines in Python made our work much more efficient and effective. We began with 7 categorical variables and 9 numerical predictors. And as you can see on the slide, there's a separate pipeline for each type of variable. For the numerical pipeline, the numerical predictors are put into a matrix, and then any missing values are replaced with the median. Then the data is normalized so the predicted predictors values have a mean of 0 and a standard deviation of 1. As for the categorical pipeline, it replaces any blank entries with 0. Then the categorical pipeline uses one-hot encoding specifically to assign integer values to these categorical variables as shown on the right with days of the week. What one-hot encoding does is it allows for the representation of categorical data to be more expressive. Many machine learning algorithms cannot work with categorical data directly. This works especially well for days of the week because there's a natural ordinal relationship between the 7 categorical variables of Monday through Sunday. One-hot encoding was very easy to implement into our code, and it just added a line to our previous pipelines. Then these 2 pipelines are combined into a final pipeline to get the code into a nice format. And now that we have used all our predictors, we're able to use feature selection to narrow down the more important ones, and Maddie will talk more about that next.
Thanks, Chase. So we used random forest's built-in feature importance to perform feature engineering on our random forest regression model. We wanted to remove unimportant predictors to decrease complexity and decrease prediction error. So prior to being able to run the feature selection model, we had to perform numeric encoding to handle our categorical variables. So numeric encoding is assigning numeric values to each level of a categorical variable. So as you can see on the slide on the left, if the origin of the load is Kansas City, the value for that feature in our data set is now 3. We had to do this for each of our 6 categorical variables. Once our data was ready to go, we were able to run the feature selection model. The graph on the right shows the results of our model, which output the importance metric for each feature. As you can see, the transcore rate had the highest value by far. In a meeting with Dr. Schubert, he suggested that we run a sensitivity analysis on different groups of features to evaluate the performance of that specific group of features. So for each group, we ran 15 iterations of the model and found the average mean absolute percent error, which are shown on the graph in black. So we started by using all features, which as you can see on this screen resulted in a mean absolute percent error of 13.1%. Then to break our features into groups, we looked for points in the results where the importance metric had dropped by over half from one feature to the next. So this occurred at the top 13 and top 11 features. We ran the top 13 features and found an average mean absolute percent error of 12.9%. And then we ran the top 11 features and found a mean absolute percent error of 12.8%. We also ran just transcore rate by itself, and it didn't perform well at all with like a mean absolute percent error of around 18%. So with these results, we ran a 2-sample t-test for all features versus the top 11 features, and we found with 95% confidence that the percent error of the top 11 features is smaller than that of all features. Therefore, we cut our features down to the top 11 and removed 5 predictors from our random forest regression model. So next, Garrett will talk about the next step we took to improve our prediction model.
Thanks, Maddie. So we used hyperparameter tuning in our model to decrease our mean absolute percent error. We focused on 6 main parameters, which are shown on the slide, but went into a more detailed analysis on 2 of these parameters. These were the number of estimators, which is the number of decision trees in the random forest, and the maximum depth, which is the longest path between the root and the leaf node. To evaluate these parameters, we started by running a random search. We specified specific ranges or options for all 6 of these parameters, and then our model tested them on our predictions. The random search helped us to be able to narrow down our ranges for these parameters. We then ran a grid search with cross-validation, which instead of sampling randomly, it tries all combinations that we had previously defined. Our grid search allowed us to narrow down some of the new parameter values. We ran 12 different combinations of these parameters using 15 samples apiece, but unfortunately, none of them were able to decrease our mean absolute percent error. As you can see from the graph on the right, we discovered that the more changes we tried to make to the default parameter values, the higher our average mean absolute percent error was. So we learned more about our model by diving into the parameters, but found that sticking to our default ones is best for our model's performance. So now I'm going to hand it off to Chase, who's going to talk about what other steps we took to improve our model's prediction.
Thanks, Garrett. So we added 2 new machine learning algorithms at the end of our random forest code to see if we could improve the accuracy of our cost prediction. These being extreme gradient boosting and light gradient boosting, known in the coding language as XGBoost and LGBoost respectively. XGBoost attempts to accurately predict a target variable by combining the estimates of a set of simpler and weaker models. Extreme gradient boosting, when compared to random forest, has advantages because it's able to run faster and has that ability to handle missing values. The difference comes from the fact that random forest uses a parallel tree growing with subsamples using bagging, while XGBoost uses sequential tree growing with weighted samples using boosting. Light gradient boosting is a more simple form of XGBoost and is also capable of handling large data sets and having accurate predictions. So we implemented both of these machine learning algorithms by using pipelines from our random forest code. When we ran this code, our runtime was definitely lower than our previous runtime, but our prediction error actually went up. And while it's good that the running time was down, our main goal is to get that prediction error down to around 10%. Both these machine learning algorithms were scrapped because of the fact that it had no effect on the prediction error, and we finalized our results after this. Jaclyn will now talk about our deliverable to JB Hunt and what we will be presenting to them.
Mute.
Thank you, Garrett and Chase. After meetings with our coordinators at JB Hunt, we decided that a Jupyter Notebook would make a great deliverable for this project. The value of a Jupyter Notebook is its ability to have breaks within the code. And within these breaks, it allows the flexibility to run one section of the code at a time. And it would enable us to describe and define the purpose and direction of that specific section of code. So with these code breaks, charts and graphs can be inserted to describe the data being worked with. This is really important for the implementation because it decreases the difficulty of following and understanding the code for a third party. This is demonstrated in the visual on the left, which displays a section of our code listing the predictors we are using for our estimation process. Below this code of predictors, there is a code break describing the code's purpose. And as you can see in the visual on the right, our deliverable will be taken by JB Hunt's data science team, who will then analyze the notebook and start to implement it into ETP in order to improve its estimation precision. From the Jupyter Notebook, we can see a direct impact from the results that this project will have, and I'll kind of sort of start to dive into those next. So as depicted between the two histograms, we have improved the precision of JB Hunt's current system. The spread of the data on the right is much narrower, with most predictions being within the $250 of error or less. You can also notice that both histograms are centered around a value of 0, which implies an accurate performance. But the narrower spread in the histogram on the right implies both a more accurate and precise performance. The real value from this comes from the percentage of over predictions and under predictions that are occurring. When an estimate is over predicted, the actual cost ends up being lower than what the customer originally thought it would be. This is seen as a positive for JB Hunt, as the customer is always happier with a lower cost. Our new system increased the number of over predictions happening from 48% to 54% of the time. The decrease in under predictions from 52% to 46% is also of value, where an under prediction means that the customer will have to pay more than what they originally agreed upon for that order. This overall improvement in both the precision and the amount of over and under predictions happening is directly aligned with JB Hunt's interests with cost estimations. So next, Garrett and our industry partner, Kyle Cratchley, will elaborate more about other impacts that this project could have.
Thank you, Jaclyn. So as you can see in the graph on the left, our model was able to increase the total number of estimations that are within 5 and 10% error. This shows the improvement in the precision of the cost estimation that our random forest is able to provide. Using the sample size of 3,367 predictions for both models, we calculated the percent of orders within these two metrics. The graph shows that the count of orders within 5% error increased from 23.4% to 33.6%, and the orders within 10% error increased from 39% to 58.6%. Our random forest model also ensures that more than half of the orders are now within that 10% error. This increase in precision will allow ICS to improve their customer satisfaction by being able to give a more precise total for specific shipments, which will hopefully lead to an overall increase in ICS's total business in the future. So ICS bases their success off of three main categories: revenue growth, retention, and profitability, which is shown in the graphic on the right. These are what they call their three pillars of success. But I'm going to hand it off to Kyle and let him go into more detail about how our project is going to have a positive impact on ICS.
Yeah, thank you, Garrett. Well, first, I really just want to start off by saying thanks for having me and congratulate this team. Again, our job well done. You know, it's been a lot of fun working with them over the last year, and this project is going to bring JB Hunt quite a bit of value. And as Garrett mentioned, my name is Kyle Cratchley. I've been with the company for almost 2 years now, and I've spent the last year working as a data scientist on our enterprise data science team. And when I first joined the company, I had the opportunity to look into this multi-stop pricing problem. But due to some other priorities, the project kind of stalled out. So it was really nice to see this team revisiting the problem and delivering a valuable solution for us. So using machine learning to improve our multi-stop pricing predictions will not only lead us to better decision-making internally, but it's also going to help us drive better customer satisfaction, specifically within our ICS business unit. And ICS has a goal to grow to a $1 billion business unit in annual revenue. And we define those three pillars of success, like Garrett mentioned previously: revenue retention, revenue growth, and profitability. And so by delivering more accurate multi-stop prices on our platform, we can continue to satisfy customers and retain that current revenue. And the goal is that our satisfied customers will then boast the cost savings of our multi-stop routes to our peers or to their peers, and our business line will continue to grow and expand. And so improving these rates will help us grow our platform and give us confidence in promoting this type of technology moving forward into the future. And again, I really just cannot stress how proud I am of this team for their hard work, their willingness to learn new things. Our leadership has been really impressed by their efforts, and we plan to implement this solution in our current process. And so with that, I'd really like to just say thank you for your time and pass things back to Garrett.
Thanks, Kyle. And I know I can say for our group, it's been a lot of fun to be given this opportunity to work on this project with Kyle and Becca, Eric, and Doug. But now I'm going to hand it over to Maddie and let her wrap up our presentation.
Thanks, Garrett. So to recap our presentation, JB Hunt's ICS division uses ETP to predict the cost of multi-stop truckloads for non-contract customers. Multi-stop transportation is used to consolidate multiple customer orders into one shipment, which is becoming more popular due to possible cost and time savings. ETP currently uses a pretty simple and outdated equation to estimate the cost of these multi-stop shipments. And JB Hunt asked us to improve the cost prediction process. So to reduce prediction error, we used a machine learning technique, random forest regression, to create a model using the programming language Python. We performed feature engineering on our model, and we were able to decrease the mean absolute percent error to about 12.5%. Our random forest model improved the precision of multi-stop cost predictions and ensured continued accuracy. It also ensured over 50% of orders are within 10% error. So with improved estimation accuracy, JB Hunt can achieve higher customer satisfaction, leading to revenue retention and growth. Thank you for listening to our presentation, and we will now take any questions.